All right, we are in the middle of how to predict the products in an equation, right? Right here. Okay, so we were looking at the solubility. We said we were going to look at solubility rules. We looked at those. We looked at the types of reactions practice. Okay, so this one we haven't looked at. If we were to look at this one, you can see the types of reactions are here. Now, if we got rid of the other side, we should still be able to predict what's going to happen based on what we know. So let me show you what that looks like. Okay, so let's say we were to get rid of this. We did not have that at all. Let's just block it off. Let's see, just put it in white, text color, yeah. Go. Okay, so according to what we know, when you are doing this, right, what you're doing is a single displacement because you have one single element and you're joining it with another something, right? So the first thing to do is to check your rules, and we're going to go there. Not just the solubility, but the other ones too. So we're going to go and get the activity series of metals. Let me see if I find one here. Activity series of metals. Okay. Find one. We have it in the PowerPoint, yes, but I wanted to see if we got any other activity series that you can. There's one in your book, I'm sure, also, but that's not what I want to do. Oh, come on, where are you? I hate when this happens. Okay, so I guess I'll just go and get that one from the PowerPoint. Okay, I'll do that instead because I'll never get there today if I keep doing this way. All right, so let's go back to get our activity series, which is in that PowerPoint. So we were looking at types of reactions or balancing equations, I think is where it was. Not a practice though, it was a, where are you? Let's say it's in here somewhere. Yeah, okay. That's the overview. I do not see. That's a practice. Nope, I am not seeing it. Why is it I can't find things when I want it? Okay. Do you guys remember which PowerPoint it was in? No, I can't find it. Okay. I think I'm gonna just, let's think. I can just look for it on the internet. That's what I'll do. Okay, there we go. There's a bunch of them. And some of these will tell you, let me see if these are the ones I want. Reactivity series or activity series. Yeah, okay. Most reactive, least reactive. But it's not giving me the part that I want. I think this is what I want. Yeah, okay, steam or acid. See, steam or hybrid, okay. H2O does not displace. Okay, so that's one. I like the one more simple one that I had. Like the one I had. It's just, I think, a little bit easier to understand. Let me look. Okay, this is another one here, but that is not the one we want either. I want the one where it said the ones that would react with cold water, the ones that would react with hot water and steam and that kind of stuff. So that's what I'm looking for. I'm trying to find that thing. And I am not seeing it. Oh, that is not the one I want. No. See, that's just talking about, that's not the one I want. I like the one I have. So I'm trying to look for something similar, but I can't remember which PowerPoint it's in. Maybe this one, let me see. Nope. Yeah, see, there's one. We could actually do this one later. Let me save this one. Go ahead, click on it and just save it for later. But these are all single displacements. Okay, so where'd it go? I hate when that happens. You click on it and it goes away. Okay. Visit. Okay. Yep, that's where it went, but it didn't really give me what I wanted. And that's because it's a PowerPoint. There we go. Okay, yeah. There we are. This is where we want. Okay, I'll just save this one for later. Okay, so we were looking at the activity series and there were some things on there that told you what was going to happen, right? So one of them said that if you were to react it with water, it would form the hydroxide, which is what we were looking for, but I could never find it. So let's just go back to the one that I had open. Okay, so, whoops, sorry, wrong one. I had a lot of stuff open and just close this. I don't need that. Don't save, no, go away. All right, I think it's this one. There we go. This is the one. All right, so I erased it on purpose because see, there's some metal and there's water. When you react these two, you're going to form a hydroxide, which is OH, right? But then you're going to still have hydrogen that you're going to make. So that's what this is. Oh, sorry. Nope. Sorry. Nope. 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 Go away. No, cancel. No, I do not. Sorry. I was doing something else. All right. Okay. So now I didn't cut it off. What I did is I changed the color. That's what I did. And I forgot about that. Okay, so we're going to change the color back to be in black, which is what I did is I just put it in white so that it would go away. Okay, so, and of course it's going to produce hydrogen, which is what we said. Now, in order for you to balance this one, right, you would have to look at the two hydrogens. Now you have three and you have one oxygen. So, what do you need? Okay, well, you look at the most complicated one first and you match it to the other one. Obviously, this one does not have enough. So we're definitely going to need to make this into an even number, right? Because the other side is even. So now we have 4 hydrogens, which means we can put a 2 here and a 2 here, and we're done. Now we're balanced. We should be. Oh, nope. Okay, so if we got 2, 2, 2, and 2, that's too many, right? But that's 2 and 2 is 4. That's 4. Yeah, so this is a 1. So that's good. This is balanced. Now, this was not a synthesis because you ended up with something else. So this is what is known as a single displacement right here. So this is what we would need to put here. So what you need to know is with a single displacement, the metal that's here has to be stronger or more reactive than the metal that's already in the compound. So the single or lonely metal, right, the elemental metal, has to be stronger than the metal in the compound. So in this case, sodium is going to replace hydrogen, but sodium is very reactive. So it's going to take the water, and remember, water is actually made of this. We kind of wrote this last time. That's what water is, right? When you decompose water, that's what it forms. So if you look at it, that's exactly what we've done here. We've taken the OH and bonded it with the sodium, and the hydrogen just bonded itself, right? And there you go. This one is a synthesis, quite obvious, because you only have one product. So if we were to categorize this one, that would be a synthesis. Synthesis, usually just you put the things that you see into one. And as you can see, sorry, that's synthesis. If you can see it, this is just one thing. That one thing makes sense that it would be CO2 because you have a carbon monoxide. So in this case, we need a 2 right here and a 2 right here, and we're done, right? Carbon monoxide with oxygen becomes carbon dioxide. Remember, there are those elements that are always what is known as diatomic, and they always appear in 2s. You never see hydrogen by itself. You don't see oxygen by itself. And so these, sorry. No, not clear that. Undo, just undo. All right, come on. There we go. So you've got Brinkelhoff. Remember, these are the elements that are always diatomic. All of these right here. Okay, they're always diatomic. So whenever you see them in an equation, they're always going to come with a 2 on it. All right, this one, remember we did this yesterday. I mean, not yesterday, but Tuesday. We decomposed it so that we know that this iron is going to go with this chlorine, and this hydrogen, right, is going to go with the sulfur. Okay, so you see how we know, because these are your ions right here. You have the Fe2 plus and you have the S2 negative, right? Oops, sorry. Plus you have your H plus and you have your Cl negative. Okay, so all of these are your ions that are present. You have to recombine them so that the iron here is going to go with something that it wasn't with already, which is the chlorine. And that's what this is. And since the ion is the F2 plus, then it's going to get FeCl2. Remember, we want to cancel out those charges. And then the last one is the sulfur, right? And the sulfur and the hydrogen are going to join and make hydrogen sulfide. In this case, it's not hydrosulfuric acid because it's in the gaseous form, and then is known as the hydrogen sulfide. Okay, so this is what is known as a single displacement. So let me get the eraser and get all this stuff out of here. All right, we got that. And we now need to make sure this is balanced, which it isn't, right? We are going to balance now. Okay, so we have 2 chlorine. We always look at the most complicated, and this one seems to be it. So the chlorine, there's 2 here, so we need to put a 2 right there, right? And now you have 2 irons also, so you need to put a 2 right there. And that pretty much balanced everybody except for the sulfur. The sulfur, there's only 1. So that actually is telling me that, see, what we should have looked at was that we would have needed a 2 before there, and that would have been would have had to be a 4 right here. And if that's a 4, that means everybody was already balanced. See, that's the thing. When you're starting to balance things, if you go up too high, and you'll see what I'm doing right here. I have gone up way too high because I'm no, sorry, not 2 there. Clear, not a 4. What did I see a 4? I'm thinking myself that is a 4, and there are 4, and that's true, but there's actually just 2. There are 4 something else. So there's a 2 here. And that's what I was thinking. There's 4 chlorines here, right? You see that? So, okay. So there's 4 chlorines now, right? So that needs to be a 4 here. And if that's a 4, then we only need a 2 there. And now we're all balanced. But you see how they're all simplifiable? And that happens sometimes when you're balancing, you get carried away and you actually put something where it shouldn't be. And so you need to now simplify everybody. And by simply putting a 2 in front of the HCl, you would have been done, right? And that would have been just fine. So it's okay. You can still balance it this way. It's the long way, but it is possible. So one of the things that you always want to be careful with is when you're balancing, you got to make sure that you are, let me clear all this junk here. Okay. That you always want to do what I said, the most complicated one first, which is this one in this case. And we could see that we needed a 2 in front of the HCl, right? And that's what we did actually. All right, so we need to place a 2 right there. And then we're done, right? Now we have 2 hydrogens and 2 chlorines, which is what we were missing. And this is a double displacement, or DR, or double replacement, because you had 2 things changing spots. This one is a decomposition, and this is hard to predict. Decomposition reactions, unless you really know what they're going to do, and you don't, that's hard to predict. But usually what will happen, sodium's pretty reactive, and nitrite, it'll just, what they call it, reduced nitrate will reduce to the nitrite, and then you get a product of oxygen in this case. So this is a decomposition. Now, let's see if it's balanced. No, it's not. So you got to put a 2 in front of this one because the other numbers are all even, right? The other O's. So now you've got 6, so you need a 2 right there, and you're done. You have balanced the whole reaction. What about this one? This is known as a combustion reaction. We're going to put a C here. Because you have oxygen, and you need oxygen to burn, right? And combustion means burning. And in this case, you have a hydrocarbon. Then what you need to do is you need to look at your CH4 and then balance the other ones accordingly. Okay, so you have 4 hydrogens, so you're going to need a 2 here. You have only 1 C, so that's balanced. So now what you need to do is count how many oxygens you have. You have 2 here, and you have 2 here, which gives me 4. So that means I need a 2 right there to balance these oxygens once and for all, right? And that should all be balanced now. All right, this is a double displacement again. So what we need to do, oh no, sorry, single displacement. So what we need to do is we need to figure out if this will happen. So iron is actually higher up than copper. So since iron is a single guy, right? Iron is going to replace copper. If it had been the opposite, it would not. All right, so since we know that, iron is going to replace the copper. And it is going to be the iron 2, because this is the copper 2. So it's going to replace 1 to 1. And there you go. So basically, no, this is the copper 1. No, it doesn't replace 1 to 1. Okay, one of the things that they tell you is if you do not have an idea of what's oxidation number this one has, because it's not bonded to anybody, so you don't know, then always use the lower one. And iron has a +2 and a +3, so we use the +2. Now we need to balance. We need a 2 here, right? And we need 2 here, and that's it, we're done. And this is what is known as a double replacement, no, single replacement or single displacement, it doesn't matter. You can call it replacement or displacement. Some people call it displacement because you're displacing, but you're also replacing, so either way. All right, this one is another one. In this reaction, actually, if you look at your periodic table, the chlorine is above the iodine, right? So this reaction will happen. And these are part of your diatomics. So you've got to pay attention to that too. So you've got a 2 here and a 2 here, and you're done, you're balanced. And this is another single displacement. But in this case, we're displacing the non-metal. You see that? This one, it's it's easy to know what this is going to do because it's single element and single element. So that's just going to combine as, this is known as a combination or synthesis. You can call it combination too. So you can just say synthesis or combination. And all you're doing is adding the 2. Now you have to remember that aluminum, right, is in group 3, right? And it's a metal, so it's a 3+. And sulfur is in group 6, and it's a non-metal, so it's a 2 negative. When we cross, you're going to get Al2S3, which is what's here. You see that? Now, what we need to do is balance. That's simple enough because they're both singles, right? So we need to put a 2 in front of that one and a 3 in front of this one, and we're done. Okay, let's clear that. This is another decomposition. See, this one, you would expect it to break into the chloride because this is the chlorate, but it didn't. Instead, it broke up, period. The KCl became one and the oxygen became another. So like I said, these are hard to know, hard to predict, but knowing that the chlorine is not as reactive, the oxygen is going to get away easily. So this is a decomposition, and that is KCl plus O2. We need a 2 in front of this one. Why? Because that other one is there, not as balanced. You always look at, like I said, you always look at the more complicated. And since this was an odd number and you had an even number here, you know you got to make this an even number. That's it. That's how you do. All right, this one's another combustion reaction. How do you know? Once again, you have a hydrocarbon, right here. And you have oxygen, and your products are carbon dioxide and water. They're always carbon dioxide and water. So if this was to be removed, you know, like if I took it and I made it white, right? And I said, what's the products? You would know immediately because you got a hydrocarbon, which means hydrogen and carbon together, and oxygen. That's always going to be a combustion reaction, and your products are always going to be the 2 things that I showed you, which are carbon dioxide and water. Now, to balance this one, there's a trick that I'm going to show you. Look at the 10 on the hydrogen. Why do we do that? Because the hydrogen here is bonded to a single oxygen. So when we look at the 10, if it is divisible by 2 and it ends being an even number, then we're good. because that would make it an even. This, and this is even over here, right? Which is not. This is a 5. So you end up with 5 oxygens and whatever, however many here, and this would never match. So what we do is we immediately double that number, okay? Since we double that number, now we have 2 times 10 is 20, so we need 10 of these, right? And then we have 2 times 4 is 8, so we need 8 of these. Okay, now let's look at this. There are 8 times 2 is 16 oxygens on that, and 10 more gives me a total of 26. Divided by 2, that gives me 13, which is what goes in front of this one. See? And now everything's balanced. All right, so that's how you do these. You can predict. All right, so what I want you guys to do, remember that one I found? I was going to use something else, but that's a good one. I want you to take your, no, I don't want saves. Okay, let me clear all of that. I want you to go back and take this one that I found. Nope, not that one, this one. There you go. And use this activity series to complete it. And you can all, and also balance it, please. Text me the results. Okay, there are 5 of them. And there are, how many of us? Let me see. Come on. Sometimes this thing gets, there we go. There's 6 of us, so that means there's 5 of us. So each one of you is going to get 1. Cameron, you're going to get number 1. Christina, number 2. Delisha, number 3. Diamond, number 4. And Ty, you're getting 5. Okay? Oh, he left. I guess I'll do that one then, if he doesn't come back. And Ty, you're getting 5, like I said. Okay, so let's do these and see what you get. Looking at what we have there. And I want you to text me the answer. If you want to do it in a private fashion, that's fine. We did these yesterday, sort of, something similar. Remember what I told you, since it's not told to you which of the oxidation numbers you have on the metals or have transition metals, assume that you have the lowest, okay? And also make sure that this reaction will or will not happen. And so if it doesn't happen, you have your very easy thing to do, because if you say NR, then no reaction means it doesn't do. Okay, somebody's got theirs, all right. Very good. Yep, that is correct. You got that one right. Good job. Somebody else has theirs. Let's see. Deletion. Oh, yeah. Yeah, but you need to tell me what's going to happen. Not just what is going to happen, but, you know, not what kind of reaction, but the exact reaction. You need to finish it. They're all single displacements. Okay. Who is this? All right. Okay, almost right. You forgot to look at your SO4. Remember when you decompose the sulfate, that sulfate's going to have a -2 charge. So you need to do accordingly, and that's all I'm telling you. So SO4 is looking like this, right? So now fix it, and you'll see. Getting close. Keep going. I had this exact number of people in reactions, but one person flew the coop. All right. Let's see, diamond. All right, let me see for number 4. Very good. Okay, so you're going to, okay, so we are trying to do sort of what you said, but you are going to actually react those. You need to react the two together. But yes, we're not doing, we're not trying to do oxidation reduction yet. So you don't need to do the ions. I was just showing you the ions so that you would know what to do once you put the compounds together. But yes, that is correct. That is exactly what would happen. But you need to put those compounds together, okay? All right. You're almost there. You're very, very close. And just like you, Alicia, you're really, really close. Oh. Yes. 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 Let's see what you mean by that, but yes, I think so. I think that's what you're saying, but let's see what you come up with once you put it up. Deletion. Okay. Let's see. Who haven't we heard from? Ty. How is it going with you? You almost there? Okay, no. Okay, no, let me show you what I mean by that. Okay, so, okay. So you've got this, right? You've got this. And just remember, we're decomposing it so that you remember what it's like. And you're going to join it with this. Right? Oh, sorry, not BH2. We're just going to join those two. So how would you join those two to make a compound? That's all. That's the only thing you actually missed. And remember, those are plus. That should be up there, but I can't do that plus up there, like in the -2 either. But they're right here, right? So I can actually put them right here for you like that, right? So those are the two you need to join together as a compound. And when you join them, you miss something. Christina, do you want to do number 1 since Cameron left us? Since you're already done with yours? Okay, thank you. It's very easy, actually. Correct. Like I said, it was easy, wasn't it? You didn't have to really do much. Yes, that is correct. No reaction. Number 1 is definitely no reaction because what you said is correct. Lead is down here and zinc is up here. And the lead is trying to displace the zinc, which is already in there, so no reaction. That is the answer, yes. That's just like your homework. This is what you have to do in your homework. Okay, so the other one was already given to me, so I'm going to put it up here. I'm trying to make it pretty, but it's not going to work. Is it reaction for 4? Yes, definitely have. And look at what it says here. It says displaces hydrogen from cold water. You see that? And we have sodium. So sodium's going to do that. Yes, Diamond, you have reaction 4. Okay, so in order for me to put these answers, I can't do it like this because they're too close. So what I'm going to do, probably put them on the other side of this thing. Okay, so over here, we know that it's NR, so no reaction for that one. But for number 2, we have, oops, sorry, lost it. Okay, hold on, clear that, because that 2 is not working. All right, for number 2, maybe I need a text box. No, because then I can't put what I need, so no. All right, for number 2, we have magnesium. That's gonna join the nitrate, sorry. And so we're gonna make magnesium nitrate plus we're displacing the silver, right? And so we're gonna do that. All right, that's gonna be a solid, obviously, and this is gonna be aqueous. All right, we think it's gonna be aqueous. I mean, we could check, but I think solubility rules say that most nitrates are soluble, or all nitrates are soluble, so we can definitely assume that that's what's going to happen. Now all we need to do is balance, and we need to put a 2 in front of that, right? And then a 2 in front of that, and we're done. I know they're backwards because they're on the other side, but that's the only place I have room for. Okay. Without covering the thing that I don't want to cover, so which is this. Okay. So number 3, how are you coming, Delisha? You almost had it. You were close. You're actually on the right track. It's just that your numbers are off a little bit. So you have to remember your ions and how you cross them, right? So when you remove that one, right, this one has to take its place, this lithium, okay? So we're removing the hydrogen from here, right? So this lithium's got to come in and say lithium. Lithium's a 1, and SO4 is a 2, so it's lithium 2 SO4. See, I didn't want to block that, so I'm just going to go the other side. Sorry. Okay, so over here, lithium 2 SO4 plus H2, right? Because this is what's being displaced. All right, now to balance it, we need a 2 in the lithium right here, right? And I think that's it, pretty much. That's balanced. Diamond has yours coming. I think you did something already. Come on, see. I think you did it already. Yeah, you did. You did it already. Yes, you got it. You already finished it. I think that I told you that, but okay, so yes, you're going to displace the hydrogen from the cold water. So just one hydrogen is going to be displaced, right? So you're going to end up with nitrogen hydroxide. I mean, nitrogen hydroxide, you wouldn't listen to me. Sodium hydroxide plus hydrogen, right? And then you got to balance. So that's the only thing. So you need 2 of these, right? And you need 2 of these, and you need 2 of those, and that's it. Then you're done. And the last one, I haven't heard from Ty yet, but if you look at it, what do you guys think? What's it going to do? What is number 5 going to do? That is correct. That is exactly right, Christina. What about you, Diamond? What do you think it's going to happen for a reaction 5? Okay. What about you, Delisha? Do you have anything on reaction 5 yet? Right. It's all right here. The answer is right here. That is correct. All right. So since, and there's 2 reasons. Since hydrogen, right, is higher than mercury, mercury will not replace hydrogen, but it also says that up to here, right, all of these will displace hydrogen from acids, but not the ones below. And this is an acid, this is sulfuric acid. So once again, no reaction. Either way you look at it, it's not going to react. So that's the answer for that one. All right, so that's how you do these. These are the single displacement. So as you can see, you can actually predict what is going to happen in a reaction based on the type of reactions they are, right? And some of these other little tools that I've given you, which is the solubility rules and this thing, which this activity series, I like the one that I have on that PowerPoint, but I can't find it. So when I do find it, what I'm going to do is I'm going to take a screenshot of it and I'm going to post that. Okay. So that way you'll have the activity series that I like. And that way you'll have all your tools that you need for your next one. Because I can't find it. I don't know where I put it. I really cannot think where that one went. But anyway, in the meantime, let's just go back to our class and see what we're doing. Okay, so we pretty much finished all of these, right? And I don't know if you guys noticed that you had a test already. One test. Let's see where they go. There it is, right there. It's coming. It's just kind of hard for me. There it is. Formula calculations. And that one is due on the 8th. I don't know. Can you guys see it okay? This test, when you are in student view, I thought I saw it, but maybe not. Let me see. I'm going to put myself in student view and see if I can actually see it. Because that's what I tend to do. And I thought I saw it, but yeah, there it is. So it is right there. So I can see it in student view. You should be able to see it, is what I was told. So you see that that test is ready to go. And you are doing formula calculations. So basically you're doing molecular formula problems. You are predicting the formula for a hydrate and molecular and empirical formula. So basically these three things that we've been doing, right, are the ones that are important for this one. And of course you got VESPR and IMF, which we did here, right? So very important. All of these things are important for reactions to happen or not happen. All right. So the next thing we're going to look at is Le Chatelier's principle. This one is a very interesting little guy. And when you look at Le Chatelier's principle, it's all about equilibrium. And dynamic equilibrium is something interesting. And I'm going to show you, because this is a link so that you can actually see the video. So here it goes.
In this lesson, you will learn about dynamic equilibrium, the conditions required for dynamic equilibrium to be reached, and examples of systems at equilibrium. Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed, there would be no change to the size of the hole. The same concept can be applied to a reversible reaction. If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there is no overall observable change. For a chemical system, such as a reaction or phase change, to be at equilibrium, it must meet two important criteria. First, it must be a reversible process. Second, it must be taking place in a closed system. A closed system is one where there is no exchange of matter, only exchange of energy. An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant. So what is happening here? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both the forward and reverse reactions are occurring. This reaction has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on top of the glass jar was opened? Please pause the lesson to think about this and resume when you are done.
Okay, let's pause. What do you think would happen? Oh, sorry, I paused it. So what do you think would happen if you open the lid all of a sudden? If they were not captive anymore, right? That means you would have an open system now instead of a closed system. So what do you think would happen? Okay, somebody said molecules will escape. Very good, especially those that are in the gas phase, right? So that means that this reversible reaction would not be, it would not take place, but it would not be at equilibrium anymore, correct? Because you wouldn't have the same forward and back reaction because the concentration of your reactants would not be there. Okay, so let's find out.
System is no longer at equilibrium as the reactants and products or matter would be able to escape the system.
Very good.
Liquid bromine equilibrates to form gaseous bromine at room temperature. Remember that this is not a reaction, but rather a phase change.
Phase change, right.
Phase changes can also reach equilibrium under the correct conditions. As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously at the same rate, there is no observable macroscopic change, but the system is in fact in dynamic equilibrium. In summary, a chemical system is said to be at equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. There are no observable changes, but both directions of the reaction are occurring. So it is a dynamic equilibrium.
Okay, that's that. So now it makes a little more sense when they call it dynamic, right? Because dynamic means moving, it's always happening, it's doing something. And yes, it is. I don't know if you remember when you took, if you've ever taken biology, there's a process called osmosis and diffusion, right? And those also reach an equilibrium at some point. But this is a dynamic equilibrium because the molecules come out, the molecules go back in, right? And it only, as many as go out need to come in. And so that's why it's called dynamic equilibrium, because it is at equilibrium, but they move it all the time. Okay. All right. So that was the idea about dynamic equilibrium in this one. Right. So let's go back to the module. Let's see, go back to this one. Okay. All right. So the next one that we're going to look at is this video, the principal video. See what it is, because it's interesting to know this. Okay.
Systems in dynamic equilibrium are very sensitive to changes in concentration, pressure, and temperature. Le Chatelier's principle enables us to predict the effect of these changes. It states that if a system in dynamic equilibrium is disturbed, the equilibrium position shifts to counteract the disturbance. For example, if more reactants are added, the system removes them by creating more products. If products are removed, the system replaces them by converting reactants. Consider the Haber process, in which nitrogen and hydrogen react to form ammonia. Le Chatelier's principle tells us that if the pressure on the system increases, the equilibrium position shifts to the side where there are fewer moles of gas, and hence a lower pressure. The forward reaction is exothermic. Energy is released when ammonia is formed. Increasing the temperature drives the equilibrium position to the endothermic left-hand side, as the system absorbs additional heat energy from the surroundings. Decreasing the temperature drives the equilibrium position towards the exothermic right-hand side. The system gives heat energy back to the surroundings. A better yield is obtained at lower temperatures, but this benefit is offset by a slower reaction. Industrially, a temperature of 450 degrees Celsius, a pressure of 200 atmospheres, and an iron catalyst is used.
Okay, So let's look at this one again one more time, because some things were said in here that were very interesting. Now, there were two conditions that we needed, right? And they were not two conditions, two things that happen when you upset the equilibrium. And that's what this is about. If you upset it, you have to predict what's going to happen. So let's listen one more time and maybe take a couple of notes right now. Make sure that you got it.
Systems in dynamic equilibrium are very sensitive to changes in concentration, pressure, and temperature. Le Chatelier's principle enables us to predict the effect of these changes. It states that if a system in dynamic equilibrium is disturbed, the equilibrium position shifts to counteract the disturbance. For example, if more reactants are added, the system removes them by creating more products. If products are removed, the system replaces them by converting reactants. Consider the Haber process, in which nitrogen and hydrogen react to form ammonia. Le Chatelier's principle tells us that if the pressure on the system increases, the equilibrium position shifts to the side where there are fewer moles of gas, and hence a lower pressure. The forward reaction is exothermic. Energy is released when ammonia is formed. Increasing the temperature drives the equilibrium position to the endothermic left-hand side, as the system absorbs additional heat energy from the surroundings. Decreasing the temperature drives the equilibrium position towards the exothermic right-hand side. The system gives heat energy back to the surroundings. A better yield is obtained at lower temperatures, but this benefit is offset by a slower reaction. Industrially, a temperature of 450 degrees Celsius, a pressure of 200 atmospheres, and an iron catalyst is used.
Okay, so there you go. So you heard all of those factors are very important in here. When you are looking at chemical equilibrium, three things can offset it. That is the temperature, remember that? The concentration and the pressure. Then we haven't looked at the temperature yet. That's why there's a second part 1 and 2. But if you think about it, when you have a concentration, that makes sense. I mean, it's like a seesaw. If you are sitting perfectly balanced in a seesaw and you get another person on the left-hand side, the right-hand side is going to go up, right? I mean, because there's more weight. That means that in order to shift that equilibrium back, the reaction is going to flip over and it will start going from where it's low, right? And it's going to start producing more. So it really doesn't shift. If you have more reactant, actually it'll stay forward because you need to produce product. If you put more product, then it's going to, once again, produce more reactant because you want to get rid of some of that product so that the equilibrium restores. If you increase the pressure, you can lower it by shifting to the side with the least amount of molecules or the moles. Like, for example, in that reaction that you saw with ammonia, you had more moles of things. It doesn't matter what, but more moles on the right, on the left-hand side than on the right. So it shifted that way because it wants to lower the pressure. If the pressure had decreased, then it would have gone the other way. Now, let's look at one last one and we're done for today, just so that we remember. And this is the last one right here.
In this lesson, you will learn about Le Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done.
Okay, what do you think would happen then? If you start removing C and D, what do you think would happen? Okay. Just kind of think about it. Okay. If you think about it, as you remove C and D, right, more A and B will react and make more C and D for sure, right? It'll try to replace it. But won't there be a time where the C and D are no longer being produced because the A and B are done reacting? Right?
The system is now stressed and no longer at equilibrium.
Yes.
To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction. When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure. The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right since there are fewer moles, 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles. So in our example, equilibrium shifts to the left. So an increase in pressure favors the side with fewer moles, and a decrease in pressure favors the side with more moles. In our next lesson, you will learn about how a system works to restore equilibrium in response to changes in temperature. In summary, Le Chatelier's principle states that when a system at equilibrium is stressed, the system works to restore equilibrium.
All right. So this next one, right? All right, if you think about it, temperature. What is temperature going to do?
In this lesson, you will learn about how a system at equilibrium responds to changes in temperature. Le Chatelier's principle states that a chemical system at equilibrium always works to restore equilibrium when it is stressed. To consider what happens to a system at equilibrium when temperature is changed, you must first consider the energetics of the reaction in question. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Let's examine this hypothetical reaction where reactant A reacts with reactant B to produce product C and product D with a change in heat of minus 75 kilojoules. This means that when the forward reaction occurs, 75 kilojoules of energy is released and 75 kilojoules is absorbed when the reverse reaction occurs. So an increase in temperature would mean that the endothermic reaction would be favored to remove the excess heat, therefore counteracting the imposed stress. Decreasing the temperature would cause the system to produce more energy, therefore the exothermic reaction would be favored. The dimerization of nitrogen dioxide to dinitrogen tetroxide is an exothermic reaction. Nitrogen dioxide is a brown gas, whereas dinitrogen tetroxide is colorless. What observations do you think can be made when the temperature is decreased? How about when the temperature is increased? Please pause the lesson to think about this and resume once you are done. A decrease in temperature favors the exothermic reaction, so more dinitrogen tetroxide is produced. Since it is a colorless gas, the mixture should appear paler. An increase in temperature favors the endothermic reaction, so more nitrogen dioxide is produced. The mixture should therefore appear darker brown. Addition of a catalyst does not affect the position of equilibrium as it increases the rate of both forward and reverse reactions. It only quickens the attainment of equilibrium. Let's return to the example of you digging a hole and your friend refilling it while you dig. Imagine that you are both given much larger shovels. The size of the hole still remains constant, but with each dig or fill, more soil is removed or filled. In conclusion, when the temperature of a system at equilibrium is increased, the endothermic reaction is favored. When the temperature of a system at equilibrium is decreased, the exothermic reaction is favored. Adding a catalyst has no effect on the position of equilibrium.
Just on the rate of reaction, just so you know. Okay, so that's it for now. We're going to look at another equilibrium at some point, but this is for now. This is all we need.
Professor
So that
here,
you,
let's talk about Le Chatelier's.
Let's not talk about that. Okay, so I'm stopping the sharing since that's it. Okay, so you're getting how that's working. Le Chatelier's is pretty simple if you think about it clearly, you know, and you're thinking about what's going on. So like pressure decreases volume, right? Increase in pressure. means decrease in volume. Therefore, you want less stuff in there, right? That makes sense. So it'll shift to the area where there's less moles. If you have more heat, exothermic means you create heat, right? So then you're going to want to remove the heat. So you're going to go to the other side and so on. So that's just all you have to think about. And then, of course, having more stuff on one side than on the other, it's going to end up you shifting to the side that has less stuff because you want to make more stuff on that side. So that's all. Simple. It's simple thinking, but it's not as simple to apply once you see it. So we're going to do that next time. All right, ladies, you have a wonderful weekend, and I will talk to you later. Bye-bye.